Now, if you are talking about Rutherford's alpha particle scattering experiment, what will the results of the experiment provide information about? Now, of the four answers, you can safely eliminate binding energy, because that one you haven't learned about. You will learn about in A2. Energy levels of electrons also not in your AS syllabus. So it's basically between size or the structure of a gold nucleus. Now, when you talk about structure, it means that in the nucleus, you need to be able to discover the existence of protons and neutrons. But if you remember Rutherford's alpha particle scattering experiment, the only thing he managed to find was that the nucleus was positively charged and very dense, meaning it's very small. So therefore, he did not manage to discover the existence of neutrons. So the answer would be C, only the size of a gold nucleus. And for this question, when we are asked about what can be deduced from the observations, number one, most alpha particles were deviated through angles of less than 10 degrees. Now, less than 10 degrees is basically also saying passing almost straight through undeflected. So the conclusion is, number one, is that your atom is mainly empty space. And then number two, you can continue to say that the nucleus must be very small compared to the atom. So that is for your part one. Now, a very small proportion of alpha particles were deviated through angles greater than 90 degrees. It means that when the alpha particles came very close to the nucleus, it was repelled. So conclusion is, you can write down here, the nucleus is positively charged, full stop. Then you can continue. Most of the mass of the atom is concentrated in the nucleus. Alright, so that is the conclusion. And the next part, they gave you a sample, okay, which is A, the path of alpha particle A. So it deflects this way. So your job is you're supposed to draw for CD and EF two other particles here. So how do you actually draw the path? Now you remember, for the path that they drew for you, remember the alpha particle starts to deviate somewhere along this point here. Alright, so what I did was I drew a vertical line so that I would know that CD would also start to deflect at about the same position. Alright, as well as EF, it will start to deflect somewhere along this position as well. So for CD, because it's further away from the nucleus compared to A, so it will be deflected less. So make sure from this point onwards it starts to deflect, but less than A, and then after that it will be a straight line. So at which point will you start drawing a straight line? Again, you refer to the path that drew for you. So somewhere along here it started to be a straight line. So similarly, somewhere along here you can also start to be a straight line, but make sure it is a smooth curve and then followed by a straight line. So, for EF, now the difference is it is below the middle point, whereas your CD and A are above the middle line here, whereas this one is below the middle line. So it will be deflected downwards, and it is closer to the center, so you get deflected more than A. So you can start deflecting somewhere here along this position. Now you deflect more, then after that somewhere along here it becomes a straight line. Now some people ask me, how do I know it turned this way? Could it turn more, or could it go and turn backwards? Actually, it will turn backwards more than this guy is deflected, but it would not go straight and turn back, because that one only applies if the alpha particle is exactly moving towards the center. Then somewhere along here it will get repelled and it will bounce back. Now this question, they gave you the alpha particle A, alright, that is actually taking this path. So first part, they want you to mark the angle of deviation of this alpha particle. So what most students do, which is wrong, is they simply use back the original path and then you just label the angle here as theta. Now you can't do that. The angle of deviation must be between the direction of the initial path. So this is your initial path, so you draw a straight line, and draw the final path here, the straight line as well. So the angle between the two directions, the final and initial, that will be your angle of deviation. And then for the second part, if you have a second alpha particle, same initial direction means to the right, and same energy r. So what will be the path of the second particle? Now remember, it is slightly above the center compared to A, so you'll be deflected less. And you remember, it starts to deflect somewhere here for A, so you will also start to deflect somewhere here for B as well. So it'll be curved, and then somewhere here is a straight line, so this is also a straight line. Now the next part, state what can be inferred about about atoms from the observation that very few alpha particles experience large deviations. That means it's referring to the ones that are deflected at angles more than 90 degrees. So it is a standard conclusion. You can say that the nucleus is positively charged, and most of the mass of the atom is concentrated in the nucleus. So it's the same as before. Now in part D, they said the nucleus could be one of several different isotopes of gold. Suggest when an explanation whether different isotopes of gold would give rise to different deviations. Now if you remember the definition of an isotope, now in chemistry you talk about atoms, but in physics you talk about nuclei. So nuclei that have the same number of protons or same proton number but different number of neutrons. Okay, now that is the first part you need to say. But also remember, the deflection is due to the charges within your nucleus. Now if all isotopes have the same number of protons, which means the same number of charges inside here, so therefore the deflection will not be affected, okay, because the deflection of the alpha particles basically is caused by the repulsion due to the nucleus. So since the nucleus has the same charge, so there will be no difference. So that's what you need to tell them. So you need to say first that the extent of deflection depends only on the charge of the nucleus. We'll stop. Since all isotopes have the same charge, there will be no difference in the deviations. In this question, we are asked, instead of giving the conclusion, they are asking for the observation. So what are the results that show evidence for the small size of a nucleus compared with the atom? So you can talk about most of the alpha particles pass straight through undeflected, okay? And the second one, the nucleus being charged and containing the majority of the mass of the atom. So you can use the other observation, which is a few alpha particles are deflected at angles greater than 90 degrees. Now let's talk about part B now. The alpha particles actually originate from the decay of a radioactive nuclide. Now suggest two reasons why beta particles would be inappropriate. Now, if you remember what are beta particles, they are actually electrons which are emitted from the nucleus. Meaning to say, when a neutron decays, it will produce a proton which stays in the nucleus, and the corresponding electron will come out as a beta particle. So why we don't use beta particles? Now, number one, since beta particles are electrons, they are way lighter than an alpha particle, because an alpha particle is a nucleus of a helium atom, so it's heavy. So if you were to calculate the mass of an alpha particle, it will be 4U, which is 4 times 1.66 times 10 to the power negative 27 kg. Whereas the mass of an electron is 9.11 times 10 to the power negative 31 kg. So the difference is about 10,000 times, right, the mass. Alright, so because electrons are very light, so the problem is this, right, the gold atoms, right, you will have the nucleus which is positively charged, but don't forget about the orbital electrons around the nucleus. Now these orbital electrons and the beta particles that are sending in are both electrons. So therefore, when they have equal mass, if the orbital electrons collide with the beta particles that you're sending in, there's a chance of them being stopped or deflected. So in other words, the beta particles wouldn't even stand a chance to come close to the nucleus. So if you cannot come close to the nucleus, how can you use it to investigate the nucleus? So that's basically what we're getting at. So the first answer is, you must say beta particles are very light, so they will be deflected by the electrons of the target atoms. All right. Now, the second reason is a bit unusual. Now, one thing that you will learn under fundamental particles, which is the last part of this chapter, is that when beta particles are emitted, there is another particle which we seldom realize, but it is there. All right, it's actually an electron antineutrino. So the electron antineutrino actually carries away some of the energy during the decay. That means when beta particles are formed, that means when electrons are emitted, antineutrinos are also emitted. And because these antineutrinos carries random amounts of energy, so that leaves the electrons with also random amounts of energy. So instead of coming out with at all the same speed, electrons usually come out with a range of speeds. So my point is, if you have a source of an alpha particle, that alpha particle source will consistently produce alpha particles of the same speed. Whereas if our source of beta particles, all the beta particles emitted from the same source have a range of speeds because of the electron antineutrino carrying away some of the energy. Now, why is that a problem? Because from the extent of deviation or deflection, we can actually make conclusions about the nucleus. So we rely on the alpha particles all having the same speed. So if they're deflected more, means it's closer to the nucleus. If it's deflected less, it's further away from the nucleus. But if your particles that you're using, like beta particles, have a range of speeds, if they're deflected more, it could be either close to the nucleus, or it could be moving very slowly, so there's a bigger deviation. So we cannot tell for sure. So we cannot make conclusions about the size of the nucleus by looking at the deviations, because the deviations depend on the speed as well as the proximity to the nucleus. So we can't make a logical conclusion. So that's the problem for us. So the second reason is, you can say that electrons are emitted, as in emitted, emitted with a range of speeds. Now for the next part, we're going to look at part B. So this is Rutherford's alpha particle scattering experiment. So why is this apparatus enclosed in a vacuum? Now remember, the alpha particles are coming out from the source, and we want these alpha particles to reach the goal foil. Now if there were air molecules inside here, because it's not vacuum, then chances are your alpha particles will collide with the air molecules along the way, which will cause these alpha particles to be either deviated or stopped. Now if they are deviated, then the deviation that we observe here is no longer due to the proximity to the nucleus, but it's due to collision with air molecules, which affects our reliability. So that's the first part here. So you would say to prevent the alpha particles from colliding with the air molecules, which may cause them to be deflected or stopped. All right, so that's the answer. Now the next part, state and explain the readings detected by D when it's moved between W, which is here, and then to X, and then to Y. So what we can say are the two major observations and the two major conclusions that we have been talking about. That means the first one you can say is that most of the alpha particles pass straight through undeflected. Then you continue the next observation. A few alpha particles are deflected at an angle greater than 90 degrees. And then you write down the two conclusions. You can say that the atom is mainly empty space. The nucleus is very small compared to the atom. The nucleus is positively charged, and most of the mass of the atom is concentrated in the nucleus.
That's all for today's video. If you are interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.